Okay, so today let's go over that check for understanding quiz that we took just to see where we were in preparation to take our first unit test. 35 questions. I'll go through each one of them. These were not necessarily in the order that you took them on the quiz because it randomizes that for you. It also randomizes the answers. What's important is the content. And do you understand the question and then what the correct answer is? First of all, here, velocity. Velocity is a vector. Remember that all vectors have a scalar, a number component, and they also have a directional component. So velocity isn't just speed, it is also speed and its direction. That's the word for word definition of what we're talking about when we say velocity. Now, acceleration. Acceleration is, by definition, a rate of change in the velocity. If you accelerate, you are changing your velocity. Keep this in mind because velocity is both speed and direction. So if you change either one of those quantities, you are changing the velocity, which means you have an acceleration. An acceleration is any change in the velocity. Now, in terms of units for acceleration, well, when we think about calculating acceleration, it's something like this, whether you use these same variables or not. It's, your finishing velocity and your starting velocity. It is the change in velocity over some amount of time. Well, in order to figure out what units are, we got to have some unit for velocity up here, whether it's miles per hour, meters per second, kilometers per hour, whatever, over some unit of time, seconds, minutes, hours, years, it doesn't matter. So let's come over here and try to find something that is a unit of speed or velocity over a unit of time. Meters per second we know is a velocity over a time. That's an acceleration. This is the same thing as that, just written differently. Kilometers per hour. We only have one unit of time here. We'd have to have a unit of time in the velocity and in the denominator of this expression. So this is not. This right here, that can be a velocity, kilometers per hour. If you're driving in Canada where they measure their velocity or their speed in kilometers per hour instead of miles per hour, that's a speed, that's a velocity over a unit of time. So this is more likely a unit for acceleration they would use in a place where they use the metric system. But that is a unit for acceleration. It's any unit of velocity over some unit of time because it's how fast or over how much time is the velocity changing. So what happens to an object's motion when the velocity is positive and the acceleration is negative? Keep in mind what these signs mean for us in physics. They indicate direction. So velocity, let's say that is the positive direction going that way. But the acceleration vector is working opposite. Well, that means the velocity is changing opposite the direction of motion. So the acceleration working opposite the velocity is going to basically work against this velocity. They're working opposite of one another. So the velocity is going to decrease. This object is going to be slowing down because the acceleration is working in the opposite direction of the velocity. Think about it this way. Acceleration is a rate of change of velocity. So the velocity is changing this way when it is moving this direction. So overall, that's going to be a smaller velocity. It's slowing down. Which of the following is a value for the acceleration of objects in free fall? That one should, well, oh, wait a minute. I've got, the number is 9.81. Which one's the better choice here is that one. Because we generally associate the downward direction being the negative direction. So acceleration due to gravity is generally expressed as negative 9.81 meters per second squared. You could, if you wanted to totally, set up your problem differently and call up the positive direction, and there might be a case where you're solving some problems that you would do that, but the best answer here is negative 9.81 meters per second. Another name for the free fall acceleration is the gravitational acceleration, because it's caused by gravity. That's what free fall means, is the acceleration, the motion is being changed by gravity. The slope on position versus time, or displacement versus time, that slope is velocity. It's how much is your distance changing over a certain amount of time. Well, that is your speed or velocity. How far are you going in a certain amount of time? Now, the slope on a velocity versus time graph represents acceleration. How much is your speed changing over time? Or your velocity changing? We just said the rate of change of velocity, that's what acceleration is. How much is velocity changing over time? That's the word-for-word definition of what acceleration is. What is the velocity of a projectile at the top of the path? A projectile is anything that's thrown or shot through the air. So we throw a baseball up in the air, and it's going up, and it's coming down. We know that up here, velocity in the y direction has to be 0, because it's going up, it has to stop. And by stop, we mean it has no velocity before it comes back down. So velocity there is 0 meters per second. Okay, so what does this graph represent? So we've got time and distance, and we said previously up here that is velocity. How much is your distance changing over a certain amount of time? Well, we see that this graph is always staying the same. It doesn't change as we go on in time. The shape of the graph stays the same. So that means the velocity, which is the slope of this line, is always staying the same. Therefore, this represents something that's moving at a constant speed or a constant velocity. What is the person doing from 5 to 10 seconds? Well, here's 5 seconds, 10 seconds. Time is still ticking, but notice the distance is not changing. Well, if the distance isn't changing, it means they are standing still. Clock is still running, but they have not changed their distance at all. Velocity is both speed and direction. Which of the following represents a velocity? Keep in mind, you just said up here, it's both speed and direction. So there's a unit for speed. There's the direction we are going. That's a velocity. This is a speed because it doesn't indicate direction. Okay? This here is just a displacement. It's how far you have gone in one direction. It's a displacement vector, but it's not a velocity vector because it doesn't tell you how long you took to do that or at what rate did you do that. Which of the following are vectors? Remember, vectors have both a number and a directional component. Velocity, we say, is a vector. Speed is not, because that's merely how fast you're going. You don't know in which direction. The same thing with distance. If I said you were 5 miles away from Centennial, that's a distance. It doesn't tell you what direction you went. Velocity is a vector. Displacement is a vector because it's 5 miles north of Centennial versus just 5 miles. Time is not a vector quantity. Speed, we already said, is not. Is acceleration a vector? Yes. Is velocity? Yes. Displacement? Yes. Can you accelerate while traveling at a constant speed? Answer is yes. Remember, velocity is both a displacement over time and a direction. Remember, velocity is also direction. So if you change your direction, you have an acceleration. You go around a curve in a car and with the cruise control set at 50 miles per hour, you have an acceleration because you have changed your direction. That, by definition, is an acceleration because you are changing your velocity. Even though you haven't changed your speed, you've changed your velocity. And that's what acceleration is. It's changing velocity, not just changing speed. What does the triangle delta mean? It means change in anything, whatever quantity you are looking at. This was kind of a thinking question. Displacement. Displacement is how far and in what direction you have moved. That's what displacement is. It is a vector quantity. It's how far you have moved and in what direction you have moved. Okay. I think we can scratch out infinity. Okay. Displacement has to be determined from some particular point. So the y-axis is not a point. That's a line. So we've got these two here. The current position of an object or a reference point. With displacement, you have to say where you are measuring from. You don't have to be there. If I had point X here and I am standing here and I move to here, in order to describe my displacement, I might say now that I am 10 meters north of X because I have changed my position and my direction from this point. Now, could I describe my point? Could my X have been where I was? Sure, but it doesn't have to be. Displacement must be from some reference point. It doesn't have to be where you are right now. It doesn't even have to be where you started. And this is going to be a very key point when we start talking about free fall problems like this, where we threw the ball up in the air and it comes down there. So I might want to talk about the displacement of the ball in relation to the ground. How far is it from the ground? Well, that's not where it started, and that's not where the ball currently is. So displacement must be a point, and you can pick the point depending upon what you want to describe about that object. I might want to describe the displacement from this point here. How far is it from this point to when it's up here or at its highest point? How far? What was its displacement from where it started? I can pick any point, but I have to have a reference point to describe displacement. A negative acceleration generally means that the object is slowing down. Which of the statements describe a vector? Well, a vector is something that has both a number and a direction. A number, a magnitude, a quantity, whether it's 2, 4, 6, 8. Magnitude is how big that quantity is, which we use numbers to describe that. So we know vectors have to have direction. That can't be correct. Direction and magnitude, size. Okay, person walks 50 north, stops, then turns around and comes 32 meters south. What is their displacement? Displacement comes from a reference point. Let's say our starting point was there. We wind up being, from the point that we started, we end up being 18 meters. Oh, you know what? I don't like this question. Oh, that's not a good question. There is no correct answer listed here. Okay, I see 18 meters. It's right there. But the way this question is worded, and this is one I just pulled out. I didn't write this particular one. We're describing displacement. Displacement is a vector, which means it has to have a direction associated with it. So yes, we are 18 meters from where we started. But in what direction? We are 18 meters north. So not a good question. It's a test question. I mean, I suppose most of you would choose that one, but it's not really a correct description of what displacement is. Okay. So here we got a ball that was thrown up in the air with initial velocity of 40 meters per second. Stops. Velocity period 0. How long does it take to reach the point back to where it was thrown from? So I want to solve for a time. And there's a couple of different ways you can do this. We know the initial velocity, you guys use that, was 40 meters per second. We know the g, or the acceleration, is negative 9.81 meters per second. I want to solve for time. And I would have to go and use my kinematics formulas. Oh, I also know the final velocity. I know the velocity here is negative 40 meters per second. How do I know that? Because I know whatever the starting velocity is at that point, because it's gravity uniformly changing the motion of this, I know that at that same or corresponding point over here, velocity's got to be the same. It's just going to be opposite in direction. So now I can do some math, and I can use a formula. I don't have those right here in front of me. I don't trust myself. There's one formula where you can calculate the time, but we'd have to use the quadratic formula. I'm like, I don't like using the quadratic formula. The whole, plus or minus square root, that's a lot of numbers. But let me show you how you can think about this. If we calculate the time to here, well, I know the time coming back down is just double that. Because it's gravity, it's going to be the same going up as coming down. So, what can I do there? If I think I can just do a straight acceleration problem. And you'll have to pardon me because I like final and initial. There's a time. Do we know what the acceleration of the ball is from here to here? Yes, we do. It's negative 9.81 meters per second squared. Do we know what the final velocity is from here to here? Yep, it is 0. The initial velocity was 40 meters per second. And we can rework this and solve for time. Okay, now notice, I'm going to get a negative, negative. Negative, negative cancels out and becomes a positive, which is good because we can't have a negative time. So it's going to be 40 divided by 9.81. We'll take the handy dandy calculator out here. 40 divided by 9.81 equals 4.07 seconds. But remember, that's the time to go up. The time to come right back down will be the same. It'll be 4.07 seconds. So we double that and we get that number right there. Okay, so standing on top of the observation deck, the Eiffel Tower in Paris is 300 meters high. So I'm gonna go ahead and like draw this. Here's one standing up here, and he drops his cell phone. Ooh, tough break. The cell phone goes down, falls 300 meters to the ground. How fast will the phone be traveling when it hits the ground? So we want to know the velocity here. We know the initial velocity in the y is 0. He didn't throw it down with initial speed. He just dropped it. When you drop something, initial speed is 0. We also know that g is that. So, okay, I need something with time. Actually, I can go kind of right back to my acceleration. Acceleration is the final velocity minus the initial velocity divided by the time. Oh, wait a minute. Oh, I don't know the time, do I? So I can't use that formula. I got to go to one of my other kinematic equations. So I have this equation, velocity to y squared I think that's how it was presented to you. Okay. I want to know how fast. I know the initial is 0. And in this case, I know the 300 meters. When I do this, I get the square root of 5886, which equals about 76.72 something meters per second. There's my answer. Okay, a freely falling object starts from rest. After falling for 6 seconds, it will have a speed of about, okay. So I know the acceleration and I know the time. I don't know a distance. So if I think about even back to my simple acceleration formula that I would have used for like one-dimensional motion, I know the acceleration is that. I want to know what its velocity is. I know it was starting from rest, so its initial is 0, time is 6, multiply 6 times 9.81. Okay. No, I'm not even going to pull out a calculator to do that. 6 times 9.81, it's got to be that. Interesting question here is that it does mention speed. If you'll notice in my formula, when I multiply this, I'm going to get a negative number because we have associated down being the negative direction. But this wasn't asking for velocity. This was asking for speed, which is just the how fast part. So that's a legitimate answer because it's asking about speed. Had this question been worded and said velocity, it'd be a garbage question and there would be no correct answer. Not really, because we would associate that as being a negative. Unless we said, "Oh, hey, down's a negative direction, and we're gonna, make it a positive." Or down, sorry, if we flipped our scales and said, oh, we're going to make down positive. Not likely. Okay, but this did ask about speed, so it's a good question. Pumpkin is dropped from a 35 millimeter. What is his initial velocity? Okay, we don't have to do any math here. Your favorite type of kinematics problem is the one where you don't have to do any math. It is dropped. It's a concept question. You have to realize, and that's what this was testing, do you realize that the initial velocity that you need is 0? Which one of these represent a constant velocity? It's going to be B. This one here shows that the displacement is not changing, which means you are not moving. Oh, wait a minute. If you're not moving, what's your velocity? Your velocity is 0. Does that stay the same? Yes. Okay. So it is both A and B have a constant velocity. Just in this case here, the constant is 0. Which graph represents a constant velocity? So the velocity is not changing. Notice we have velocity on this graph, so the only one where the velocity, the numbers on this axis are not changing is D. What is happening in D in this equation here? Okay, so D, we've got this line here. That's part of the graph we're looking at. Stationary. Well, no, because I see at D, my distance is still going up, so I'm not stationary. This is distance in time. And the slope of my distance in time isn't changing. It's staying the same, which means my velocity is staying the same. I am not changing my speed, as opposed to this one here, where the slope of the line is changing, my velocity is changing. C has an acceleration. Fast, steady speed, moving away from the starting position. Slower, steady speed, moving away from the starting position. Well, it's certainly moving away from the starting position either way, because our distance keeps going up. It's not like this one where we're coming back to our starting position. So it's got to be one of these two. Now, both the speeds are steady. In terms of the graphs that we see here, I'm going to say it's a fast, steady speed, because that's a pretty steep slope of a line. So the distance is changing very quickly in a small amount of time. So a steep slope of a distance time graph means, man, you're going pretty fast. A slow, steady speed would have been something like that there, a low slope distance versus time graph. Okay, ball is thrown downward. Now this is a little bit different. Got a guy on top of a roof, and he throws a ball downward. Probably was trying to hit the physics teacher that was walking down there on the street. But we throw it down with initial velocity. Now, why did I call that negative? Because I threw it down. I'm going to associate the down with the negative direction. The acceleration is gravity. Right? I know the time. After 2 seconds, its velocity will be. Well, I can just use a basic to figure out its velocity. I know the acceleration is negative 9.81. I want to know what that velocity is. I know the initial was a negative 25, and I know it's 2 seconds. So I'm going to do my math here. I'm going to take 2 times 9.81. Okay. And then I'm going to have to add to that my 25. My velocity is about 44.6 meters per second. Oh, wait a minute. Dang, I didn't read it quick enough. Oh, I wasn't careful. Bad physics teacher. That's why he's getting hit with the ball down here. This question is asking about velocity, which you must indicate direction. The ball's going down, and we called down the negative direction, so we got to say the velocity is that. Okay. An object that is freely falling is acted upon by the force of gravity alone. For now, we're going to say that is true. There will be air resistance that we will kind of sort of have to consider later on. But for now, we basically said gravity is the only thing changing the motion of the object. An airplane accelerates down a runway from rest at 3.20 meters per second for 32 meters until it finally lifts off the ground. Determine the distance traveled before takeoff. Oh, which equation is? So I need an equation that's got distance in it. Oh, sorry, couldn't read that. Can't be that one. There's no distance in there. There's no. Oh, that's the distance. That's the distance. The x is my distance, or what you would, I think in your kinematics equation you were giving them, it's delta x. Okay. We know the acceleration. We know a time. We don't know a final acceleration. So that one's not going to be a good choice for me. Which equation is appropriate? I got these two. I got distance. Say, I guess we're assuming that the initial velocity is going to be 0 because the plane's not already moving before it goes to take off. But we don't know its velocity before taking off. So we're going to have to use that one right there. That's the only one that has the variables in that I can use to solve the equation. Okay. So we want to find the acceleration of the car in here. We were given we got a final speed, we got initial speed, we got a distance. We want to find the acceleration of the car. So we don't have a time. So I can't use that. Oh, do I know the final speed, final velocity? Yes. Do I know the initial velocity? Yes. Do I know the distance it took? Yes. So there's my best choice. Okay. Ball was thrown up and it comes back down. What's the speed of the ball when it gets right back to there? It's got to be the same. Because gravity is changing the motion of the ball, you know it's going to be the same going up as coming down. That's one of the beauties of free fall problems, or when it's only gravity affecting the motion. Whatever the ball was here, it's going to be the same here. So it was the same speed as when it was thrown upwards. Okay, this one I had a little bit of a typo on because I changed this question. I pulled it out of the test bank, and so this was marked incorrect on some of yours. But once again, it's formative grade. That's not the important part. The important part is, do you understand the concepts? Where would you have greater acceleration due to gravity, the Earth or the Moon? Notice I put a picture in there. You'd have greater acceleration on the Earth because the Earth has more mass, and mass is what causes that pull of gravity. So the Earth is going to pull you more than the Moon. Man drops his camera off the top of the oil derrick tower at Six Flags. Which of the following kinematic equations would he use in order to calculate the speed the camera was traveling when it hit the ground? All right, well, we don't know how tall the oil derrick is. So anything that has a D in it, all right, that's not going to help me. That's not going to help me. Okay, so it's got to be one of, oh, wait, this is not too bad here. Oh, wait a minute. They're not giving us any numbers here. Oh, we have to make an assumption here. If we did, I guess they're saying if we did know the distance, which one could we use? Okay, well, he drops. Initial velocity is 0. We don't know a time. We don't know a distance. Let's see. Oh, I don't like this question because it asks us to make some assumptions. If we knew the distance, we know the initial because it was dropped, and we know the acceleration, but we wouldn't know a time. So still thinking probably not this one. We don't know the final speed it hit the ground with. We know the initial speed. We know acceleration. We know a distance. So it's probably going to be this one if we make the assumption that we know how high the tower is. Didn't give it to us in this. Not a great question there. Which of the following statements applies to the motion of a ball rising and falling in free fall? Okay. The ball has constant acceleration as it moves upward. Yes, because it's caused by gravity. The ball has constant acceleration top of its path. Yeah, because acceleration is caused by gravity. The ball has a constant acceleration as it moves downward. Yes. The acceleration is the same because it's caused by gravity, and gravity, no matter where you are on this path, works the same. So it is D. So that's kind of a long, lengthy explanation. I will do my best to try to let you see what you answered on the quizzes. I'm trying to figure that out, how I can email you a report, but you should kind of sort of remember what you answered. So if you have any questions, you can come back over to the chat, and or you can email me, and I can clarify some things for you.